Kirchhoff actually has two laws. I'm going to be looking first at Kirchhoff current law. Some people call it Kirchhoff's. Is that what you guys called it in physics?
Back in high school.
Kirchhoff, yeah. Kirchhoff, Kirchhoff. KCL. It's probably Kirchhoff, who knows? So the abbreviation for that KCL, it says KCL, Kirchhoff current law, Kirchhoff current law. And what Kirchhoff or Kirchhoff said, the algebraic sum of the current entering any node is 0. That is Kirchhoff current law. So for example, if this is a node again, a point that connects two or more elements. These are elements. And we said, we know this current going in is 5 amps. We know this current leaving is 3 amps. And let's say I define a current going this direction. We'll call it I. And I say, can you tell me what I is? Kirchhoff current law says if you take all the currents entering the node is 0. Well, you say, wait a minute. This is really leaving the node. Well, if it's leaving the node, what can you do with it? You can change the direction of it to what? Going into the node, and what's the value now? -3. Just change the direction of it. So if we take these three currents and add them, we go 5 plus a -3 plus I has to equal to 0. Five plus a -3, that's a 2, plus I is equal to 0. I will have to be what? -2. So if the current is leaving the node, we make it a negative value. If it's going to the node, we make it a positive value. Me personally, I have no problem with it, but I like to use my own notation. I said if we sum, that's Kirchhoff current law, KCL, it says if you take all the currents, if you add the summation of all the current going into the node, it should equal all the current what? Coming out of that node, leaving that node. The current in equals the current out to any node. What goes in must come out. That's it. So if I do that, I can look at that picture I did there, and I go, well, let's look at it. What's going to that node? I got the 5 amps, and I, and what's leaving that node? The 3 amps, the way I did it before. I had it going out. Move the 5 there, what's I equal to? 3 minus 5, which is what? -2. So I tend to do them that way. Instead of the algebraic sum of all the currents entering a node is 0, I go the current in equals the current out. Let's take an example and see if we can solve it. All set, Nick? Mm-hmm. Okay. Everyone's all set? So let's take this circuit. Let's go back and see if you remember. This source is called what? DC. Independent voltage source, right? It's a DC source, has 10 volts, yes. But independent voltage source. We have a resistor on the top. I'm not giving you the values. We don't know. It's called R sub 1, resistor 1. We have a resistor on the side here called R sub 2. All I know, there's a current coming down through R sub 2 here of 2 amps. That was given to me in the problem. We have another resistor here, R sub 3. And I have an independent current source going upward of the value of 5 amps. And there's a current labeled as I. Here's the question. Compute the current through resistor 3 R3 if it is known that the voltage source supplies a current of 3 amps. That's what the question is. The voltage source is supplying a current of 3 amps. So what does that mean to me? Here's what I know. This voltage source supplying, by the way, when the voltage source is supplying current, that means the current coming from the minus to the plus of 3 amps. Now let's keep looking at that circuit. When it hits that little corner, what's going to happen to that current? It's going to turn right, continue to go in this direction of how much? Still 3 amps. So now I see a node right here. Kirchhoff current law says what? The algebraic sum of all the current entering a node is equal the algebraic sum of all the current leaving that node. Or the algebraic sum of all the current entering a node is 0 if you label leaving the node as negative value. The current in equals the current out. What is going to that node? I see 3 amps going to that node. What else do you see going to that node? 5 amps, good. What's leaving that node? 2 and what? I. 3 and 5? Is that 8? Equals 2 plus I. And the current I is going to be what? 6 amps. So we just calculate that current through that. Is it always going to be that simple? No, but that's a start. So that's what Kirchhoff current law. The algebraic sum of all the current entering a node is 0. The algebraic sum of all the current entering any node is 0. Or again, you can say the current in equals the current out to any node. Kirchhoff also has one law for voltage. It's called Kirchhoff voltage law. Let's see what that one is. Bless you. Kirchhoff's voltage law, and that's known as KVL. And the law states that the algebraic sum of the voltages across any closed path is 0. The algebraic sum of all the voltages across any path is 0. Closed path. So again, the closed, I mean, you start from one point, you end up at the same point. Let's take this example. Let's say we have an element here. I don't know what's in it. And this is labeled plus to minus. We'll call it V2. That's element 2. We have another element here. We'll call it 3. And let's label the voltage minus to plus, V3. And let's put 1 here. This is element 1. And let's label the voltage here. What should we call it? Plus to minus, V1. Notice that's a closed path. If you start from this point, from this node, you can go around and come back to what? The same node. So what Kirchhoff said, if you travel in a closed loop like this, and if you add all these voltages, they should add up to a 0. The one part he didn't mention anything about, notice, let's say I'm traveling in this direction. Do you notice anything as you enter this source here? You're entering from which end? Negative end. You're entering this one from which end? Positive. This one from what? Negative. So one of them has to be positive, one has to be negative. You can't just add all three of them because you have different polarity. So you get to choose. It really doesn't matter which one, but most math books, circuits book, they'll use if you enter the negative as positive and if you're entering this as negative. But it doesn't matter. You can do it either way and your answer will not change mathematically. So if you want to stick with our book, you go, well, I'm entering the minus, that's a positive V1, this voltage. I'm entering the plus, that's a negative V2. Keep going. I'm entering the minus, that's a positive V3. The result is what? 0. If you do the math here, it says V1 plus V3 equals what? V2. If you're like me, I go, you know what? I don't know why we're flipping them. You enter the minus, you make it a plus. You enter the plus, you make it a minus. Why not just leave it if you enter the minus as a minus, enter the plus as a plus? So this becomes what? Negative V1 plus V2 minus V3 is equal to 0. And if you move V1, V3 to that side, what do you have? V2 equals what? V1 plus V3. Is that the same answer? Look right here and look right here. Same thing. So it really doesn't make a difference which one you call plus, which one you call minus, as long as you're consistent. Mathematically, your answer will be the same. Let's take an example on Kirchhoff voltage law, KVL. Let's say I have this example. Independent voltage source of the value of 5. There's another independent voltage source of the value of 7. We have a resistor here of 100 ohm, and this is the value of Vx. I have two questions for you. There's a current going to be traveling this way. Can you tell me what that current is? So the question is, find the voltage Vx and the current I. Notice I do have a closed path here. There we go. I said I have a closed path because if I start from here, I can travel this way, come back down to the same spot. You can see. So KVL says sum of the voltages in a closed loop. If you add all the voltage in a closed loop, the result is 0. So I'm entering the minus to plus. What do you want to call that? Positive or negative? Negative 5. I'm entering the minus to plus. That's what? Negative 7. I'm entering the plus to minus. That's what? Positive Vx is equal to what? 0. So what's Vx equal to? 12 volts. I got the voltage, I need the current. How do we find the current?
V over R.
Okay. Using what? Ohm's law? V equals I times R. He's looking right there, going, I know the voltage here. The voltage is what? 12. I'm looking for the current. The current through there, which happens to be the same current through the whole loop. It's only one loop. Do we know what R is? 100. What is I equal to? 0.12 amp. One more thing I want to add to this while we're looking at it. If you add the negative 5 and negative 7, that'll give you what? Negative 12? So you can actually take this equation and rewrite that as negative 12 plus Vx. You agree with that? So if I take this resistor and I put 100 ohm here, that's the resistor, that's Vx. Instead of having two sources now, can I just put one source of the value of 12 here? Because if I do KVL here, I'm going this way. That's what? Negative 12 plus Vx equals to 0. Isn't that the same equation like that? So when you have voltage sources in series, you can add them if they're pointing in the same direction. If one negative to positive, one positive to negative, you know this will be negative, that will be positive. You have to do what? Subtract them.
If you have multiple resistors, you just add the values together.
Well, that's coming up. It depends how they're connected. If they're in series, yes. If they're in parallel, no. You might have a combination of both. We'll do that shortly. But if you see sources like these and they have the same direction, minus to plus, those are connected in series. You can add them into one source. If one of them is backward, then you can subtract them and you take the direction of the bigger one. Let's take a bigger problem here than this one. And maybe we can apply both KVL and KCL. I don't know. Let's see. This is minus to plus 4 volts. don't know the value of that resistor. Independent voltage source of 36 volts here. Can't tell what this value here, but let's call this resistor R sub 1 or R sub 2, whatever you want to call it. R sub 2, because that's 1 maybe. And let's call this voltage V2. We have another resistor here. And I know the voltage across that resistor is plus to minus 12 volts. I have some elements. I have no idea what's here. Some element. All I know, the voltage across that element is plus to minus 14 volts. So it's not a voltage source. It's not a current source. It's not a resistor. Something else there. Otherwise, we'd throw in probably one of these. I have another one here. Another element. I call this one what? V2, let's call it minus to plus, let's call that V3. I have a source here. And I don't know if the value of that is given or not. Give me a minute, I'll look in the problem and see if it's given. And it's connected like this. And this is resistor 1, 2, 3. This is resistor 4, so we'll call this V4. And they'll label plus minus. And the question is find what? V2. What else we got here? What is Vx? VR2, which of course R sub 2, I get that. And the voltage labeled Vx. Where the hell is Vx? Oh, Vx is labeled right here, the voltage. Plus, minus Vx. Maybe I'll highlight these two. I guess I wasn't planning on making a mistake today. Where's my eraser? So Vx is labeled right here. That's V. That's 12 volts. Try to make the ones you're trying to find in red so you can spot them. So these are the ones I want to find. V2 and Vx. Let me find V2 first. Notice I see a closed loop right here. Can you see it? Try not to highlight the whole thing. Can you see that closed loop right there? So KVL says sum of the voltages in a closed loop is 0. Let's say the current is going to be going this way. So KVL at loop 1, I1, that means loop 1. If I'm going this way. Let me start with this one. I'm entering this plus to minus. That's a negative 4. Entering this minus to plus. That's plus 36. Entering this plus to minus. That's what? Minus V2 is equal to 0. Come back here. So you do the math. V2 equals what? 32 volts. Now Vx. Well, you need to measure Vx. And I don't know if you did that in the lab or not. Did you measure voltage in the lab yet? You have a digital multimeter in the lab. You take a wire. You take that wire, you attach it right here. Plus, you take the minus, you attach it right here. And that's your meter. We call it M4 meter. And that will measure the voltage right there. So by hooking the meter here, guess what you did? You created a closed loop right there. So if I follow that closed loop right here, that's my closed loop. If I apply the same technique, sum of the voltage in a closed loop is 0. Sum of the voltage in a closed loop is 0. Let me begin with this one. So KVL 2 here. I2, 2. That's the second one. Maybe 1 and 2. So you'll know which one. Let's begin with this. That's minus to plus. 32 volts, right? Minus to plus, we use what? Positive 32. Plus to minus, we use negative what? 12. Plus to minus, we use a negative 14. Plus to minus, we use negative Vx. So what is Vx equal to? 32 has 20, 20 minus 14, is that 6? Six volts. So I'm using sum of the voltage in a closed loop is 0. Let's try another one. Here's my circuit, different example. 6 volts. 8 ohms. 10 ohms. 4 ohms. And 2 ohms. And finally here we have a current source. It says find Vx. They give me one more thing, that the current going this way. The current going this way is 5 amps. And what they want to know, what is the voltage here? Vx. This is I sub S, source. We don't know what the value of it. They're not asking for it, but maybe we can find it too. So we have a source pushing, and they're not telling us how big that source. They're saying, all I know, the current going this direction is 5 amps. can I find Vx? I'm going to change it. Find, bless you, Vx and I sub s. I want to find both of these. I know it doesn't ask for this, but maybe I can do some quick calculation. If there's current going this way of 5 amps, what's going to happen to that 8 ohm resistor? It's going to mark it voltage here plus to minus. And what's the value? Ohm's law says V equals I times R, right? 5 times 8, 40. So I came up with this by saying the voltage across the 8 ohm resistor is equal I times R. I is 5, R is 8, that's 40 volts. And if the current's going to the right, it's going to mark the resistor plus to minus. Plus on this end, minus on that end. Maybe I can find what we'll call this V1 is. How? There's a closed loop right there, see it? I can go inside this one. Let's call it loop number 1. So if I do KVL for loop 1, this is loop number 1. Sum of the voltages in a closed loop is 0. 6 minus 40 minus V1 is equal to 0. V1 is equal to what? Is it negative 34? What does that mean, negative 34? It means this end is 34 higher than that end. This end is 34 higher than that end. That means the current is really going up, not coming down. The current here is going up. So there's a current going up in this direction. We'll call it I1. And do we know what that current is? Ohm's law. V equals I times R. What's the current up? Plus to minus here. What's the current plus on this end, minus on that end? 34 equals I times R, which is 10. So I sub 1 equals what? 3.4? So that current going up 3.4. There's a current going this way. There's a current coming up. That means something has to leave. Let's call this I sub 2. I can do KCL at the top. KCL says if you take all the current entering that end should equal all the current leaving that end. What is going to that node? 5 and 3.4. What is leaving that node? Only I sub 2. So I sub 2 equals what? 8.4 amps. Let me clean that circuit because it's getting messy here a little bit. Redraw it and write everything that I know so far. This is what I know. If I'll make it bigger too. 6 volts here. I got a resistor of 8 ohm. I got a voltage here of what? 40 volts. I got a current in this direction of what? 5 amps. Make it a little bit bigger. We have a 10 ohm resistor. We agreed we have a voltage plus to minus because V1 was negative. What was V1? Negative 34. That means plus to minus 34 volts. That's what we had. And we have a current going up of what? 3.4. I got the 4 ohm here. I got a current in that direction of 8.4. Now let's continue with this. Can we calculate what the voltage right here is?
Oh, yeah.
Which is what? I like that answer. Oh yeah.
I times R.
I times R. I times R. 8.4 times 4. 33.6. Can I get this voltage now? We'll call it VZ. We'll call this loop loop 2. KVL at loop 2. Sum of the voltage in a closed loop is 0. I'm entering the plus to minus. Plus to minus, what are you going to use? Minus 34? Plus to minus. Minus what? 33.6 plus to minus VZ is equal to 0. VZ equals what? 67.6 with negative. Again, if it's negative, that means what? If I reverse the direction of it, it's really what? Plus here, minus there. Right? Of 67, not negative. That's what that means. These two connected in parallel should have the same voltage. Right? So Vx shouldn't be 67, should be negative 67. Should be the same as this end, marked in the same direction. And if you don't believe me, do KVL there. Take the mess out. Do this as a third loop. I want to prove to you that the voltage here is the same as VZ. There's loop 3. If I do KVL on loop 3, that says sum of the voltage in a closed loop is 0. There is a closed loop, a closed path. I'm entering the negative VZ. The negative, so that's VZ. I'm entering the plus, that's negative Vx is equal to 0, which tells me Vx equals what? VZ, which means Vx equals negative 67.6. We said this voltage is wrong, it's negative, right? That means there's current going which direction? Upward. Because because the plus on this end, the minus on that end. The current has to be going upward. Can we get with that current? I sub Z. 67.6 ohms law, voltage divided by the resistor, which is 2. V equals I times R. What's 67? 67.6 divided by 2. 33.8. And we know this current going in, that's 8.4. You see it? 8.4 going in. 33.8 going in. This one going in, all of them going in according to the picture. KCL of the last node on the top, KCL, says all the current entering a node should equal all the current leaving that node. And what is going to that node? 33.8. What else going to that node? 8.4. What else going to that node? I sub S should equal what's leaving? 0. So I sub S is going to be negative, and let's add them. That's 2, 9, is that 42? So negative 42.2 amps. So I'm using KVL and KCL together back and forth. I have more examples to deal with KVL and KCL as the problem gets more complicated, as you have dependent sources, but I'll put that on the next video.